This is the OpenHBI course Linked Data Engineering, Lecture 2, RDF and RDFS. In this part of the lecture, we will talk about the representation of simple facts with the help of the resource description framework RDF. Okay, RDF, as you see here in the semantic web layer cake or semantic web technology stack, is embedded in two other blocks. Here it's the blue block, and below the RDF block, which represents the information exchange in the semantic web, you have several serialization formats, like for example RDFA or Turtle or XML, which we talk about later. And on the other hand, you will also be able to give structures or schemas according which RDF facts can be built and represented. And this is up above. There is RDFS, as you see here. So RDF is embedded here in the blue block of the semantic web technology stack. Let's have a look at it. By the way, the main example that we will use for RDF is the planet Pluto. Oh yeah, pardon me, it's not a planet, it's a dwarf planet, so it's no planet anymore, but we will come back to that later. First, let's focus on RDF. So, the resource description format. What is a resource in that sense? So a resource can be anything which can be uniquely identified and is referenceable with the help of a URI. Or if you look at it in an international context, then it's an IRI, an international resource descriptor, or something like that, or a resource identifier. That's the resource. Then we have the description, which means with RDF you describe your resources, and you do this usually with the help of properties and relationships that can be between these resources, and they can be represented or are represented as a kind of graph. We have already seen that. And then you have a framework, which means based on the web protocols, like for example HTTP, and of course other protocols and standards like the URI, XML, Turtle, JSON, and so on. You have a combination of web-based protocols which form the basic building blocks and framework of RDF, so it relies upon other kind of web technology. And what is also very important, you have a formal model, a formal semantics. And this formal semantics gives RDF more power than a traditional data definition language, because you will be able to draw valid and sound conclusions. We will come back to that later on. So how is knowledge expressed in RDF? Usually it's a list of RDF statements. And we have already seen RDF follows a very simple schema, these so-called RDF triples, which follow roughly the structure of a sentence in natural language, which consists of subject, then some property, and then some object, or subject, predicate, object. So it's a quite similar way to build sentences to represent facts. We have seen this in the previous part of the lecture. Okay, so here is the typical way to build an RDF triple or an RDF statement. Usually you have a subject which is represented as a URI. So this is a resource about which you make a statement, about which you give some information. Then you have a property which describes the kind of information you give, and also the property is given as a URI. And then this property is assigned some kind of value, which might be another resource. Then you represent this resource with a URI, or it can be a literal, for example, a string value or something like that. And we have two different kind of representation schemata. One is somehow text-based serialization, and the most basic one is the so-called N-triple serialization. You see it here. There, URIs are simply represented by the URI string, which are embraced by these angle brackets. And you see here a literal as an object value, here 1930. This is a string, and strings usually in N-triple serialization are written in double quotes. And the triple itself then is closed by a period at the end. So this represents the same fact that is represented below in the graph representation, where you have two nodes. First node, that is the subject node containing the URI, here of our example Pluto. And then you have an arc, or an edge, to another node. And the other node here is a literal node, so it contains simply the string 1930. And the edge itself is labeled with a URI, which is the URI for discovered, which means Pluto has been discovered in 1930. So this is then the graph representation for exactly this kind of fact. So we have learned there are two different kind of RDF statements. One is based on literals and the other one is based on URIs as objects. So literals itself describe values, so they don't have a separate existence and they cannot be referenced from outside somewhere. So usually you represent them at the spot where you need them. So it's different, for example, a URI of course points at some resource on the web. It should be dereferenceable, therefore it can be at any point in the web. So this is something which points from your knowledge statement somewhere else and connects knowledge, therefore. So this is a very interesting means to represent knowledge which is more global and not only locally arranged. Concerning the literals, we have learned that, for example, written in double quotes, literal usually, this is the default setting, is a character string. But sometimes you also want to express a value which has a certain specific data type. And therefore you are also enabled in RDF to use data types, which means you use typed literals. And as types, you can use all the types that have been defined in the XML schema definition language. So you see here the namespace for the XML schema definition language, and you see here on the right side a rough list of the possible data types that you can use. So for example, if we look at the core data types, we have string, we have Boolean, we have decimal and integer for some kind of numbers. There are several floating point numbers, like for example double and float. Then there are special data types for dates, or there are limited ranges for integers and stuff like that. So there are various kind of types that you can use. How do I type a string, a character string, literal, in RDF? Just have a look at the examples that are given here. So for example, the first example tells us that semantics, written in double quotes, should be assigned a definite data type, and which is here the character string. So it's a string. Of course, string, the data type, is represented via a URI, which in the end describes exactly the XML schema data type. The second example, here you have a number 1161.00. So this is a floating point number. So therefore, we type this string with a specific data type, which is a floating point number, also derived from XML schema. And the third one, you see that this is simply a date, and here you use the XML date schema type. In this way, you are enabled to express typed literals. Another variant, for example, would be if you are using a character string and want to say in which language the content of the character string should be interpreted. You see this then here. This can be denoted with the help of so-called language tags. So language tags denote the natural language of the text. And you do this simply by adding behind the quoted string these ampersand sign, and then you use a 2-digit identifier. This is according to an ISO standard. So for example, DE for Germany, EN for English, and there are 2 character abbreviations for every kind of country or language that you want to represent here. Okay, I have given you a link here to the available data types. Simply click on the link and then you see the definition of all the available data types for RDF literals. So we had URIs, we had literals. And there is one special thing among RDF. You do not always need a URI. For example, if you want to make an assumption about something which you cannot identify directly, but you want to make a statement about the existence of something. So there exists something which has been discovered in 1930. There exists something, the same thing that has been discovered in 1930 has the discoverer with the name Clyde Tombaugh, or the URI Clyde Tombaugh. We know that this, of course, is Pluto, but you don't have to express it. And therefore, RDF provides a special means, and this is the so-called blank node. A blank note does not contain a URI, therefore it simply denotes the existence of an individual with exactly these specific attributes, but without providing an identification or reference, which means blank notes, of course, cannot be referenced from outside. So you only can use the blank note right on the spot here. Nevertheless, it's quite useful because you can make these statements about the existence of something without specifying exactly the individual you are referring to. So this, we will see that, is quite comfortable and comes quite handy sometimes. Okay, how do I write RDF statements, RDF triples then in the web? So there are several serialization formats. We have learned about N triples. This is the most basic format, but this is a bit uncomfortable because, for example, if you want to express lots of facts about the same subject, you have to repeat the same URI over and over again. Therefore, there is another more comfortable language which is called Turtle, and Turtle enables you with something which is called syntactic sugar. So there are some means that provide better handling and better serialization in a more concise way, in a more readable way compared to N triples. So we will have a close look on Turtle. So all our examples will be based on Turtle. Nevertheless, for the data exchange between applications, for example, there are also other kind of formats. There is an XML serialization. It's called RDF XML, or there is a JSON-based serialization, which is called JSON LD to comply to the JSON format, for example, and to enable also legacy applications to communicate here with the help of RDF, which are able to, for example, use JSON. So there is JSON LD for that. And there are even more formats. You can look them up if you are interested in. For us in the course, the most important one is the Turtle format, and everything then will be in Turtle. But first, let's have a look at some of the different formats. So we start with the N triples format, or N triples notation. We have already seen that. So URIs or IRIs are written in angled brackets, literals in quotation marks, and the triple usually ends with a period. That's it. So we have here the two facts. Pluto has been discovered in 1930, fact number 1. Second fact, Pluto has the discoverer Clyde Tombaugh. Second fact, so the first one with a literal as an object, the second one with a URI as an object. Quite easy, but you already see here that, for example, we have to repeat the URI of the subject all over again. And here we are using, for example, URIs from DBpedia. So what we have to repeat is the prefix for DBpedia. So this http://dbpedia.org/resource/ has always been repeated here. And of course, this is some kind of redundancy. We will see about that later. Here is an example for the RDF XML notation. You see that here you require even more space. For better readability, I have used here different colors for the simple parts of RDF. Let's have a look here. So where is the subject? The subject is buried deep down here in the code. We have here an RDF description. Then we have the attribute RDF about, and there is the subject Pluto. Then you see here both of the properties that have been provided. We have one property which is called discovered, and we have one which is called discoverer. And then we see here the object discovered 1930, so 1930 is a simple character string, it's the literal here, or Clyde Tombaugh, it's a URI, and the URI has to be written with an attribute here, RDF resource equals, and then comes the string or character identifier of the URI. So this is the XML notation, and I think you would agree that, for example, if we have to read lots of facts about Pluto in a way like that, for a human this is quite uncomfortable and it's really difficult. Then we have the JSON LD notation. So some of you who are able to read JSON will immediately recognize what is what here. So for example, here we have the subject in the first line, then we have the property each in the second line, and then here we have the object, which is once a value, and in the other, for the second example, it's an ID. So this would be the JSON LD comparable serialization of the fact we have seen here. And finally, we have a look on turtle, so our first of many turtle examples. Turtle is the abbreviation for terse RDF triple language notation, and as we already know, it's an extension of n-triples. And only as one of the many possibilities that you have, first thing what you can do, you can define so-called prefixes, and this is simply for abbreviating the triples, how you write them. So here we define a prefix which is called DBO, and DBO then stands for the prefix http ://dbpedia.org/ontology/. So this is then DBO. And you see then here in the third and in the fourth line that our subject Pluto, and then comes the property, and this is abbreviated with DBO, and then you make a colon, and then comes the rest, so a so-called relative URI. And what the turtle parser does is simply it substitutes the prefix here, and then you have the entire URI again. So this is something to abbreviate the code. The second thing that you see here, we can define a base URI, which means each and every relative URI in the text which does not provide a prefix then will be interpreted with a prefix I define as a base. The base here is dbpedia.org/resource, so which means, let's look here at the line 3 and 4, we have Pluto in the third line, and in the fourth line we have Pluto and Clyde Tombaugh. These are relative URIs, and they will be extended with the base URI, which is then dbpedia.org/resource. So you see here, if we read the two lines, Pluto has been discovered in 1930, and the discoverer of Pluto is Clyde Tombaugh. This is much easier to read than the other kind of serializations, and this is also the reason why we are using turtle in the future. Okay, so much for turtle right now. We will see then in the next part of the lecture more RDF constructors and more RDF syntax, and everything will be in turtle serialization.